So welcome to this video. In this video, I'm going to talk about the Weierstrass preparation theorem. So this is a theorem that basically describes how does locally an analytic hypersurface looks like. Okay, so an analytic hypersurface is the zero locus of an holomorphic function, and we are going to see locally how can you find nice coordinates so that it looks like the zero locus of a certain kind of polynomial in one variable. Okay, so I'm gonna go through the statement as written here. So we start with a holomorphic function defined in a neighborhood of the origin. So I wrote here a polydisk of radius epsilons, and the epsilon is small. Assume it is holomorphic and it vanishes at the origin. And suppose you pick one axis, let's say the last one, to be generic enough so that the function is not identically zero on that axis. Okay, so if the function is not constant equal to zero, then you can do this for the generic choice of axis. Okay, so you pick the Zn plus 1 to have that property. And then the statement says that in a neighborhood of zero, you can find D, where D is some number, some integer, some non-negative integer, a1 up to ad of functions depending only on the first n coordinates. Okay, so we have a function in Cn plus 1, they do not depend on the Zn plus 1. Okay, and another function which depends on all the coordinates. Okay, these are all holomorphic and they satisfy the following properties. First, h does not vanish at zero. Okay, so that's one of the properties. And the other properties is that all the other functions, a1 up to ad, they do vanish at zero. So this thing here. Okay, so those do vanish at zero. And then you can write your function f of z1 up to zn as a polynomial in Zn plus 1 with coefficients, the first d functions I mentioned, which only depend on z1 up to Zn. So this is a polynomial in Zn plus 1, but its coefficients are holomorphic functions of the remaining coordinates times h. Okay? And given that h does not vanish in the origin, then this thing, the zero locus of all this thing here in these parentheses actually controls the zero locus of f near zero. Okay, so this thing here is what is called the Weierstrass polynomial of the function f in the coordinates zn plus 1. And basically, a consequence of this Weierstrass preparation theorem is that the zero locus of a multivariate holomorphic function coincides with the zero locus of this Weierstrass polynomial. Okay, so that's I wrote that here in this second line. Here you can see. And before we embrace in the proof, I want to go again to rewrite this in a nicer notation, just so that in the proof we can use it. Then we still need to do some preparation. Some preparation before starting to prove it. And I also want to make a few extra comments. So for simplicity, I'm gonna refer to the Zn, to the z1 up to Zn as z. So it's just a notation, and w is gonna be Zn plus 1. Then we can write the statement, the final part, as being that f of zw is a polynomial in w with coefficients holomorphic functions of z times the function h, which does not vanish at the origin. Okay, so this is the statement. And now I want you to think of what this is saying. So suppose that you pick z equal to 0. So if you pick z equal to 0, you have f of 0w is just a function of w, and this looks like w to the d times h of 0w. Okay, so at z equal to 0, the zero locus looks like w to the d. Okay, so it's a degree D um, 0, a 0 with multiplicity D, which I've drawn here in red, and I'm gonna now do in orange above. Okay, so that's this degree D0. And what the rest is saying is that as you deform to some constant z, different from 0, but suppose it's constant, then you are in this vertical dashed green line, then these d zeros, they may split into some other zeros. But overall, the number of zeros counted with multiplicity should remain to be d, because you can imagine some degree argument that you measure the degree in this in w around here, the origin, and you get d, and if you move slightly, just a little bit, the degree cannot change because it varies continuously, and therefore you must have, you must have those zeros there also. Okay, I don't know what I did here. There is a knee that appeared. I'm sorry. Maybe I can erase it. No, I cannot. Anyway. Okay, so this is what I wrote here in green. As you go away from the origin, the multiplicity d0 may split into different d0s counted with multiplicity, of course. Okay. And another way to interpret this is to look at what I did here in blue as the projection to the z-axis. So if you look at this projection, it is a branch cover. Okay, so it is branched when the zeros clash with each other. Of course, at 0 it is very branched. Okay, and as I said in the beginning, this gives the local form or what is called an analytic hypersurface. And importantly enough, it is controlled by these by the zeros of a polynomial in W. So that's maybe the first indication that if you try to do that complex geometry and algebraic geometry have many things in common. Okay. Okay, so before we embrace in the proof, let's follow this preliminary computation that I'm going to do here. And this preliminary computation basically reads as follows. So you pick two functions of one variable, chi, say, that is holomorphic, and you want to compute the integral over some simple closed curve gamma of g over f times df d chi d chi. Okay? By the residue theorem, this will be the sum over chi i's, which are the simple poles inside gamma, of simple poles of this function here inside the red thing, and then the residue at that pole. Okay? But you can see that this function here has singularities if only at the points where f vanishes. So at the points where it is singular, f should vanish. Okay? But then a computation which is done below shows you that in fact at any zero of f you actually have a simple pole, and the computation is basically as follows. You pick f, you write its Taylor series near chi 0, one of these zeros. Of course it starts at 1 because you have a 0, so important there. It starts at 1. Then you differentiate it, and then you compute the f d chi over f, and you arrive at a simple 0 like 1 over chi minus chi naught. It's basically this computation. And then if you multiply by g and you take the expansion near chi naught, then of course you get the g of chi naught there. So this guy is the residue of g over f df d chi at chi naught. Okay, so that is an important point, and therefore you can write this integral using the residue theorem as stated here. Using that information, you can take the sum over the zeros of f inside gamma, and you evaluate g at those zeros because that's the residue. Okay, so that's the important computation that we will use. And now we are going to see how to prove the Weierstrass preparation theorem. Okay. Okay, so recall what we are trying to do. I'm going to write z in this manner, w like that is going to be zn plus 1. And we know that f does not vanish identically along the w axis, and it vanishes at 0. Okay, and then the point, the theorem says that we can write f in this manner, like a Weierstrass polynomial in w here times the function h that does not vanish at 0. And we know that these coefficients here are holomorphic functions of z. Okay, so first of all, if I can pick my function to not be identically 0 along the w-axis, then I can pick a small enough epsilon greater than 0 such that f of 0 epsilon only has 1 0 when w is less than epsilon, okay, when the absolute value of w is less than epsilon. So this is basically saying that along here, along this region here, sorry, and the other region below also. So let me try to put, so it's basically saying that here, in all this region here, in that axis, oops, that was not intended. Anyway, I'll put it back in, don't worry. Okay, so, oh, actually I can do undo. That is that hypothesis. Okay, so, okay, so that basically says that here, in this region where the z is 0 and the absolute value of w is less than epsilon, the function f only has 1 0, which I placed there in red at 0. Okay, there it is. And now we can further go by continuity along these black lines here, go plus or minus epsilon along here. So we can go epsilon, no, delta, I called some other small number, delta. I can go away from z equal to 0 in those lines that the function f continues to be non-zero. Okay, so I draw delta here in blue. So we know that f is non-zero in this black line here and this black line there. Okay, so which are actually polydisks, but anyway, in one dimension less. Okay, so now I'm going to pick a fixed z in this region with with the norm of z less than delta, and I'm going to let denote by w sigma 1 up to sigma d the zeros of the function w goes to f of cw. So there are these guys that I wrote here, sigma 1, sigma 2, sigma d, are the zeros of the function of w that keeps z fixed and evaluates f. Okay, so these are the zeros of the function along this vertical line here. Okay, then I'm gonna write my candidate to be the Weierstrass polynomial. So this is the candidate to be the Weierstrass polynomial, which is this guy here, which is basically the polynomial that has zeros precisely there. By the way, and these zeros, I'm counting them with multiplicity, okay? So I'm counting them and listing them with, if there is 1 0 that has multiplicity 2, then I'm gonna write it in this list twice, okay? Counting. Okay, so back from this small technical problem. So remember, we were in this sigma 1 up to sigma d. These were the zeros of this function here, but counted with multiplicity. Okay, that's counted with multiplicity. So for instance, if there was a 0 here that had multiplicity 2, then I would list it here twice, and then p would have exactly the correct multiplicity there. So p is going to be our candidate to be the Weierstrass polynomial of f in w. Okay, so clearly it has the same zeros of f in that region exactly with the same multiplicity. So it has the same zeros with the correct multiplicity. So you can define this quotient here, which is the quotient by the two of f by p, and this clearly is non-zero at the zeros of f or p because they have there the same multiplicity. In particular, it is non-zero at the origin. Okay, and then okay, our f can be written as the product of p by h and we do have that these guys, each of them is holomorphic in W. P is this polynomial, H, because of what I said before, is holomorphic in W, but we don't know if they are holomorphic in Z. Okay, remember that the Weierstrass polynomial, its coefficients, which are functions of Z, need to be holomorphic in Z. That was part of the theorem, and we need to prove that. And the same thing for H. H needs to be holomorphic in Z. Okay, so let's see the proof. Let's start with the simplest one, which is H. So it is here. So what we can do is to write H in this region using the Cauchy integral formula in the second coordinate in W. Okay, W takes values in C, and we can integrate over a circle of radius epsilon to write H of ZW using the Cauchy integral formula in this manner. And what is the advantage of this? Is that now we are integrating over this region here, where the norm of Z is equal to chi. So I wrote this here. And in that region, neither F or P have zeros, okay? Neither F or P has zeros by the way we chose it. Remember, in this picture here, it's exactly this black line here and this black line here. It's when the norm of Z is equal to, when the norm of chi, which is W here, is equal to epsilon. And there are no zeros in either F or P, because they have the same zeros. So indeed we can write H in that way, and it will be holomorphic in Z in that region, because this guy here is holomorphic in Z. So this guy here also needs to be holomorphic in Z. Okay, so that is the proof. Now let's go back to P, our Weierstrass polynomial. We write it, remember it was this product, we write it as a polynomial in W in this way, and of course the coefficients are these guys, which for example the first one is just minus the sum of all of them, which is this, and all of them are powers, sums of powers of the values of the zeros, okay? And what we need to do now is to prove that these guys here are holomorphic in Z, which is the same thing as saying that these guys here with these different powers are holomorphic in Z. So that's what we're gonna do now. Okay. Okay. So that's what I have written here, except that I did not finish writing. So in order to show that POC is holomorphic in Z, we must show that these AKs, which are these powers, are holomorphic in Z. Okay, so the sigma i's z's are the zeros of this function as a function of W. And so by that preliminary computation, the sum of sigma i's of z, so I'm going to try to write this as the residue of that function that I'm going to plug in the residue theorem. So this thing needs to be the value of a function that I'm going to write as in front of 1 over f df d chi, because this selected a sum over the zeros of f of the values of this function, which is precisely what is here. So this is just an application of our preliminary computation. Okay, so the preliminary computation we did above gives you this, and then we need to look at this, because now if you look at this equality here, on the right hand side, you have something that is clearly holomorphic in Z, because again in this region here, when W is equal to, I'm here calling it chi, so I'm going to write chi equal to epsilon, chi equal to epsilon. In this region where I'm integrating, this function f has no zeros, okay? Remember again, it's those black lines where the function has no zeros. So these guys here are holomorphic in Z, and so is this guy over here on the left-hand side, okay? And so that is basically the proof that these guys here are indeed holomorphic in Z, and that finishes the proof of the Weierstrass theorem, the Weierstrass preparation theorem. And just one comment that I said in the beginning is that this number of zeros need to be constant using this degree argument, but you can actually see it from here because you have this here an holomorphic function in Z that gives you an integer, so it must be constant. Okay, so that is a consequence of part of the computation. And this follows from using here the power k equal to 0, where you are just counting the zeros of f inside the region enclosed by the norm of w equal to chi. And again, the norm of w should be the norm of chi. Okay, so thank you for the attention and see you next time.